Let's learn regarding the module 4. The module 4 has vector space, subspace, orthogonality, and the next it would be determinants. Linear algebra part. So first let's see what is a vector space. A vector space is a non-empty, just as we know that collection of elements. Which kind of elements? It has real numbers. So a vector space is a non-empty set. Let's refer it as V. It has some objects and the objects are referred as vectors on which on the components or on those vectors the two operations addition and multiplication by a scalar, especially a real number. Scalar has to be a real number, holds good. A vector is one which is having both magnitude and direction. Let's take a vector u and then the v. Then by law of triangle, u plus v is given by. And we know there is a law of parallelogram. And even if we have three vectors, then u, v, the sum of them is u plus v, and even there is a w, then the things holds good. So to learn bit more regarding these vectors, so a vector as we represent it, a vector v, a vector space is represented by usually as it is containing vectors. So it has been referred as v. So let's say it has a vector u, v, w, etc. Then to obey or to satisfy the additive and multiplication properties, it should have the properties. Let's have a glance on these properties. So the axioms it has to satisfy is u and v. If they belong to v, the set, then u plus v should also belong to v. As we say, the u plus v. If u and v are there, u plus v should also be there in v. Then u plus v should be equal to v plus u, as it is true with the real numbers. And associative property with respect to addition, if we have three numbers, then the sum of them should be also there in v. Then it has to satisfy zero vector in v such that u plus 0 is equal to u. And if there is u in our space set, then minus u should also be there in that v such that u plus minus u should be equal to 0. Then the scalar multiple of u by c, represented as c into u, should also be there in v. As we can see, c into u, even c into v, c into w, all these all components should be there in v. Then the next properties with respect to addition, c into u plus v, the distributive property and unity property. Anything multiplied by 1 is the same number, so it has to be true with respect to v. U into 1 or v into 1 or w into 1 should be equal to the same value. Then to learn these vector spaces, the most important vector spaces are r raised to 1, r raised to 2, r raised to 3. These are the important spaces and these run up till r raised to n. So what is this r raised to 1? R raised to 1 means it is a vector having only one element. R raised to 1 is having only one element. So whatever it can be. It can be 1, 2, or whatever. Similarly, R2. R2 means R2 should be this like 1, 2. It is a two-dimensional Here, the R2 indicates R1 indicates a single dimensional vector. R to the power 2, that is R2 indicates two-dimensional vector. A two-dimensional example can be our xy plane wherein x and y can take any values. So let's draw a plane wherein x is a horizontal axis and y is a vertical axis having four quadrants and any point on these quadrants. It may be in 1, 2, 3 or 4. It is belonging to r to the power 2 or we can say it belongs to r2. Likewise, r3. R3 is a three-dimensional component or three-dimensional vector. The three-dimensional vector having x, y and z components or having three components. The components are usually the real numbers. Then R4 is having four components in it. Likewise, R to the power n will have n components in it. So the components can be like x, y, z, w, t or anything, or the values of x, y and z could be any real value like 1, 2, 3. They may be increasing, decreasing in any fashion, they may be variable. So they can be 1, 2, 3, again -1, 1, anything that could be. So a vector space is a set of vectors, is a set having some components. So it can be a single dimensional. The example could be a point. Then it can be two-dimensional, having two components in it. It can be three-dimensional, four-dimensional, and it can have n components in it, making it n-dimensional. The vectors can be represented either in a row form or in a column form, as shown. So they can be a column vector or it can be represented by a single. And even there can be R0, which is nothing but a point, which is having only a point representation. So to understand these in a better way, so if it has to be a vector space, then to understand them, it should satisfy the three. Like, let's learn these three examples. The first one is the infinite dimensional space. The infinite dimensional space r raised to infinity. Its vectors have infinitely many components as in x, 1, 2, 1, 2. It can be a repetition or a different value. So the number of components in r raised to n as we saw, so we should be n. And with respect to all those components, x plus y, the additive and the multiplication by a scalar should be satisfied. Then the second example is the space of 3 by 2 matrices. As we know 3 by 2 matrix, the 3 by 2 matrix, the 3 by 2 matrix having some components, let's say 1, 2, 3, 3 by a 3 by 2 matrix as we see. The 3 by 2 matrix having 6 components, will satisfy. So 3 by 2 matrix have 6 elements. It can be represented as 6-dimensional kind of a thing because it has 6 components in it and it satisfies a plus b is equal to b plus a, the commutative law. And if we multiply, we know that if we multiply this matrix with any of the scalar value, then even that will be the 6-dimensional, in the sense that is also having 6 components in it. And certainly that should belong to the real R6. So of course, as 6 components will be there, it belongs to R6. And even There is a 0 also in the matrices. And if we add 0 matrix, if we add that 0 matrix to each of this element, then we get the same element. Hence, it satisfies both the properties. Then, the next one is with respect to functions. With respect to functions, let's consider the variable as x, and if that x is varying from 0 to -1 or +1, if that's x is varying from 0 to 1, then let's say one function is f of x is equal to x squared, another one is g of x is equal to sin x, then their sum is f of f plus g of x is equal to x squared plus sin x, and all multiples like 3x squared, because we know that f of x is x squared. Multiplication by any scalar, that scalar could be anything in between minus infinity to plus infinity. So it could be 2, 1, -1, anything. So 3x squared or minus x squared or whatever the value should be, anything c into x squared. That is, c into x squared should be there in that space, in that vector space. And the sin x can be multiplied with again any of the scalar value from minus infinity to plus infinity. Then minus sin x, if it is -1, sin x minus 1. Sin x multiplied by -1 is equal to minus sin x. These all should be there residing in the vector space. A vector space examples are these all. A vector space should satisfy, or if it is r to the power of whatever the value, it should have those many number of components. It should obey the additive property, multiplication by the scalar property. The example could be a matrix, and with respect to functions also, it is true over the range, or the range can be anything from minus infinity to plus infinity also in some terms. So that is regarding the vector spaces. I hope vector space, if we brief it, a vector space is a set, a space set, a vector set, a vector space set having some components. Let's, as they are having some direction, because we are especially learning with respect to vectors, so we are representing it as a V, then it can have some components, and with respect to these components, the additive property and the multiplication by a scalar property are always satisfied. Those axioms are to be satisfied. And usually these components are real numbers. So we are calling it as r raised to 1, r raised to 2, like this. Now let's go for learning what is a subspace. A subspace is one, just like a subset. A subset is one which is having few components of its parent set or its main set. So in the similar way, a subspace is one which is having some components of the vector, main or parent space. So vector space part can be a subspace, but to be a vector subspace, it should satisfy the axioms. So a vector subspace is a non-empty subset which satisfies the requirements. The requirements are linear combinations, means the additive and the multiplication properties should be satisfied. Means if a subspace if a subspace contains x and y components of the parent vector space, then the subspace should contain x plus y and a 0 in it by the first property. By the second property, if we multiply any of the component x or y by means of a scalar, and here the scalar can be anything. The scalar can be anything from minus infinity to plus infinity. if we multiply any of the component of that subspace by a scalar, then even that should belong to that subspace, or the subspace should contain that multiplied or multiplicative value. A vector subspace is a subset that is closed under addition and multiplication. Then to learn this one, let's see an example. So the example is a simple two-dimensional kind of a vector. So let's consider r to the power 2 or r2, let's refer it as. It's a xy plane, and as we know that the xy plane x is along x is a horizontal axis and y is a vertical axis, and it has four quadrants: the first, second, and third. So we all are familiar with these properties. The first quadrant wherein both x and y are positive. In the second quadrant, x is negative, y is positive. In the third quadrant, they all are negative. And in the fourth quadrant, again x is positive and y becomes negative. And R2 is a vector space. As R2 is a vector space, to learn the subspace, then let's check whether one of the quadrant, let's say the first quadrant, is it a subspace? So to be a subspace, it should satisfy two properties as we know, as we are aware of. Then when we go for checking the properties, we know that in the first quadrant, if we take any value for x and y, they would be positive. And let's say it is our subspace, subset, let's say first quadrant, subspace. So let's refer it as subspace first quadrant is equal to, will have the x and y. And of course this x and y are positive and involve 0 also in it, as it has to satisfy the property of addition. So when we take 2 points, both, let's say there's 1, 2, 1 and 2, and let's think that another point is, let it be 3 and 2, or 3 and 1. When we consider these 2 points in the first quadrant, these should be there. Of course, as first quadrant itself is the subspace, these all belong to that space, that subspace. Now let's check whether the addition of these two belongs to that subspace or no. So 1 plus 3 is 4, 1 plus 3 is 4, and 2 plus 1 is 3. And of course, addition of two positive numbers has to be a positive number, and this 4 and 3 belongs to this first quadrant. So we satisfy the first property. Then let's see the second property. In the second property, we have to pick one point and multiply by a constant c, and this c can be anything from minus infinity to plus infinity. No problem if c is equal to anything positive. If c is positive, then this multiplicative property is satisfied. But if the c is negative, if c is negative, let's take that the value of c is equal to minus 1. If the value of the c is minus 1, and if it is multiplied with this first point, then we get the result of this one as minus 1. We get the result of this one as minus 1 and minus 2. And this minus 1 and minus 2 doesn't belong to the first quadrant. They belong to the third quadrant. And in our subspace, we have taken only the first quadrant as are subspace and multiplication by a scalar that is negative, let's say minus 1, will not contain that multiplied values on the in the first quadrant. So the second axiom, the second property is not satisfied. As second property is not satisfied, it is no longer a subspace. Then even if we consider the subspace as quadrant 1 and 3 also, we failed in one of the property. So just check that one in the notes and understand what is a vector space and subspace. Thank you.